Hello class, I hope you're having a wonderful day. Today I would like to talk about two topics from Chapter 8. First, let's talk about torque. Torque describes the tendency for a force to cause a rotation. So the higher the numerical value of torque, that means it's going to have a higher tendency to cause a rotation. Now, kind of the opposite of that would be an object's rotational moment of inertia. And whenever we're talking about an object's moment of inertia, what we're doing is describing its resistance to a rotation, okay? And so, for example, if we were going to go purchase some nice sports car wheels, obviously it's going to be important to reduce the mass from the stock wheels that you have on your sports car. But what is more important is the value of the rotational moment of inertia. So how we're going to calculate that is the distribution of mass with respect to the axis of rotation. So we're going to calculate three problems today. The first one here, I'm going to read you the problem. We're going to write down some knowns and draw a simple picture and then calculate the value for the moment of inertia of the object. So on number one, here we go. A solid rubber ball has a radius of 41 centimeters and a mass of 1.12 kilograms with an axis of rotation through the center. Calculate the object's moment of inertia. So, like I mentioned, the first thing we're going to do is record some knowns and then we are going to draw a picture. So, the problem tells us that the radius of the ball, so I'm going to say radius of ball is equal to 41 centimeters. Now, we know that we're required to put this unit in meters, okay? So we're going to perform some dimensional analysis here. We're going to treat units as algebraic quantities. So we're going to multiply by 1 meter divided by 100 centimeters. So this will be equal to 0.41 meters. Next, the mass of the rubber ball is 1.12 kilograms, and it says it has an axis of rotation through the center. So what let's do is draw a picture. Here we have a ball or a sphere. Here's the center of my object. And right here we have the radius as 0.41 meters. And the problem tells us that the axis of rotation is through the object's center. So let's go ahead and label that. So axis of rotation. All right. So for different geometries, we're going to have a different equation for the moment of inertia. So for a sphere with an axis of rotation through the object's center, what we're going to have is I is equal to 2/5 times the object's mass times the radius of the object squared. So you can see just by looking at the equation that the distribution of mass, so the distance that the mass is located with respect to the axis of rotation, is more important than the mass itself. So as I mentioned earlier when we were talking about sports car wheels, while mass is very important to that wheel, what's more important is the rotational moment of inertia. So for all high quality sports car wheels, you can usually find the moment of inertia for the specific wheel that you're interested in purchasing. Now, a lot of your cheapo depot, bottom of the line wheels, the companies don't publish this data because they don't want to tell you what the moment of inertia is because the value is really bad. So, okay, back to this. Right here, we have 2/5 times the mass. The problem tells us that the mass is 1.12 kilograms. The radius of our sphere is 0.41 meters. And that value is squared. So let's go ahead and grab our calculator here. According to the order of operations, we're going to have to square our radius value. So radius squared, you can see that here. So 0.41 squared is going to be 0.1681. So let's go ahead and rewrite this here. I've got 2/5 times 1.12 kilograms. And then numerically, I have 0.1681. And units, we have meters squared. So remember, not only are we squaring the numerical value, we are also squaring the unit value, okay? So let's go ahead and take the product of these values here. And our moment of inertia for this solid rubber ball is identified by capital I. This is moment of inertia. And this is going to be 0.0753 kilogram meters squared. So whenever we're describing the moment of inertia of an object, it's going to be in units of kilogram meters squared. Okay, let's move on. Let's take a look at number 2. So a metal hoop has a diameter of 2.5 meters and a mass of 1.3 kilograms. With the axis of rotation through the central diameter, calculate the object's moment of inertia. So once again, we're going to record some knowns, and then we are going to draw a simple picture, okay? So the mass of the hoop, 1.3 kilograms. The diameter, so let's go ahead and do a diameter symbol. Diameter of the hoop is 2.5 meters, and so we're going to have to identify the radius. So 2.5 meters divided by 2, you know the radius is half of the object's diameter. So this is going to be 1.25, and we have units of meters. Now, we need to draw a simple picture here. Okay, so there's our hoop. There's the center of the hoop. We need to identify the axis of rotation. So I'll go ahead and record that. Axis of rotation, and then we have the radius of the hoop. And the radius of the hoop is 1.25 meters. Okay, so the book describes this as thin hoop of radius r, and its equation is I is equal to mr squared. So since we have different geometry here than we did in our previous problem, we're going to have different equations, okay? So right here, the mass of the object is 1.3 kilograms. The radius is going to be 1.25 meters, and we have to square that. So let's go ahead and grab our calculator here. Remember, according to the order of operations, we're going to have to square this value first and then multiply by the mass. So remember, once again, we are not only squaring the numerical value, we're squaring the unit value. So what I've got is 1.25 meters squared. This is going to give us 1.3 kilograms times 1.5625 meters squared. Let's go ahead and take the product of these two values here. So times 1.3. And the moment of inertia for our hoop, and I'll use a subscript here, hoop is equal to 2.03125. And we have units of kilogram meters squared, because remember, we're describing the rotational moment of inertia. So this is the resistance to rotation. So as we increase the value for radius, so the distance between the axis of rotation and where our mass is located, our resistance to rotation will go way, way up, okay, because we're squaring that value. All right, let's complete one more together. So, number 3, a vehicle has an aluminum drive shaft with a length of 1.34 meters, a diameter of 8.65 centimeters, and a mass of 9.8 kilograms. The axis of rotation for the drive shaft runs through its center, and so the problem wants us to calculate the moment of inertia for the drive shaft. Now, many of you might be asking, well, what is a drive shaft? Well, what we're describing here is the shaft or the rod that connects the transmission to the rear differential on a rear-wheel drive vehicle. So what we have an engine. I'm just going to draw a simple side view here. We have an engine, we have a transmission, and then we have the drive shaft. I'll just identify that with a capital D there. So we have the engine. Attached to the engine, we have the transmission. Then attached to the transmission, we have the drive shaft. And then the drive shaft is connecting the transmission and the rear differential. Okay? So what we're looking for is this guy right here. We're going to calculate the rotational moment of inertia for the drive shaft. So let's record some values. Here we have the length of the drive shaft is 1.34 meters. So I'll put a dimension here. And then we have a diameter of the drive shaft is 8.65 centimeters. We know that we're going to have this unit in meters. So once again, we're going to perform some dimensional analysis. We're going to multiply by 1 meter and divide by 100 centimeters. My units of centimeters will cancel here. So that means the diameter of the drive shaft is 0.0865 meters. And what we're going to have to do is we're going to have to divide this by 2 because we need the radius of the drive shaft. So I've got 0.0865 divided by 2. So I've got radius of drive shaft is 0.04325 meters. And the mass is 9.8 kilograms. Okay, so what I want to do is draw the drive shaft here, okay? And so what we have, then we'll draw a break line here. We don't need all of that business, okay? So here's the center of the drive shaft, and here's the axis of rotation right here. Okay, all right. So in this situation, we do not need the length of the drive shaft since the axis of rotation is right here and we're spinning that like this. So let's say this expo marker is my drive shaft. We're spinning it like this, okay? And I'm showing the axis of rotation right here. All right, so now we need the equation. So I have the rotational moment of inertia of the drive shaft. This is equal to 1/2 times the mass times the radius squared. So this is going to be 1/2 times the mass that is given to us in the problem. We've got 9.8 kilograms. The radius right here, remember, we are required to use units of meters, and we're using the radius, not the diameter. So radius is 0.04325 meters. And once again, we are required to square that value, okay? So remember, the distribution of mass, whenever we're describing the rotational moment of inertia, the distribution of mass is more important than the mass itself, okay? So 0.04325. We're going to square that, and that is going to give us, so I've got 1/2 times 9.8 kilograms times 0.0018706. And now we're going to have meters squared. Now let's take the product of these three values. So I'm going to multiply my calculated value for radius squared in units of meters squared, okay, times 9.8, and then I'm just going to divide by 2 there, and then this gives us rotational moment of inertia for the drive shaft is equal to 0.00916 kilogram meters squared. Okay? All right. So that will do it for these three problems. Remember, Anytime we are going to describe the moment of inertia for an object that's rotating, so the distribution of the mass is more important than just the value of mass, okay? So hopefully me working through these three problems has helped you today. If you have any questions, as always, you can send me an email, you can give me a call on my office phone, or you can send me a message over Canvas. Well, I hope you have a great day.